Hi friends, this is Viswanath, chemistry faculty. Now see the forensic laboratory questions answers. Which one of the following diagrams correctly shows the band energy diagram of an eccentric semiconductor? Here 4 graphs are given. We should identify correct one. CB means conduction band, VB valency band, IB impurity band, E means energy. So for these 3 bands we have to find the correct energy order. First of all, eccentric semiconductor means 14th group elements. Silicon germanium elements can conduct electricity when these are doped with other elements, other substances. Such type of semiconductors are called eccentric semiconductors. That means after doping other substance, then only they conduct electricity. So these are called eccentric semiconductors. In these type of substances, valency band having lower energy, and then impurity band, and then conduction band. So option C is the answer. Next, see the next one. The number of inner orbital and outer orbital complexes from the list given below are respectively. See here, 5 species are given, 5 complex ions are given. In that inner orbital complex and outer orbital complex we should identify. In which case we can get inner orbital complex? In the given species, ligand is a strong ligand, then we can get inner orbital complex, or otherwise ligand is weak ligand, we can get outer orbital complex. So how can we decide strength of the ligand, whether it is strong or weak? Based on spectrochemical series. That means based upon the spectral values of various ligands, we can arrange them in the increasing order of ligand strength. That arrangement is called spectrochemical series. See here, based on ligand strength, which is decided on the position of ligand in the spectrochemical series. So based upon the spectral values, we can arrange these ligands in the increasing order. So in that order, lower ligands having the position of a ligand is lower position, then it is weak ligand. Higher position means strong ligand. So we can find the inner orbital and outer orbital complexes. These are the 5 species. Here ligand is cyanide, CN. Here fluoride. Here ammonia, here ethylene diamine, here H2O. In these 5 ligands, strong ligands are Cn-, ethylene diamine, NH3. These 3 ligands are strong ligands, and F-, fluoride, NH3 are weak ligands. So strong ligands means they can form inner orbital complexes. Any unpaired electrons are present in the central metal atom, they undergo rearrangement. Then orbitals present in the inner shells can also participate in the hybridization. Hence we can get inner orbital complex. Now outer orbital complex, these are weak ligands. In this case, any unpaired electrons are present at the central metal atom, they do not undergo rearrangement, they remain as it is. Hence, only orbitals present in the valency shell can participate in the hybridization. Therefore, we can get outer orbital complexes. So, how many inner orbital complexes means 3, outer orbital complexes means 2. What is the suitable option? Option A. Next, match the following. Complex ions are given and hybridization, their magnetic behavior we should match. See here also same thing. For these type of questions, we need not find oxidation state of central metal atom and writing the unpaired electrons to calculate magnetic moment, all these things. It is time-taking process. In this type of competitive exams, in a simple way, we can find the answer. That is based on strength of the ligand. Strong ligand, rearrangement is possible, then they can exhibit diamagnetic. Weak ligand, rearrangement not possible, then they exhibit paramagnetic. Here Cn, strong ligand, NH3 strong ligand, F6 weak ligand. So strong ligand means inner orbitals can participate in the hybridization. Weak ligand means outer orbitals can participate in the hybridization. For this, answer is option D. See this, FeCN6 3- inner or strong ligand. D2sp3 6 ligands, coordination number is 6. Hybridization is D2sp3 paramagnetic. Then this one NH3, for this also it is also strong ligand NH3 ammonia, hybridization D2sp3 and diamagnetic. Based on this strong ligand we can predict hybridization and then immediately write the unpaired electrons present in the central metal atom. From that we can get paramagnetic. Don't calculate whether it is the magnetic moment of these complex ions, how many electrons are present, that is enough to get the answer. Next, this is weak ligand. Weak ligand means and 6 coordination number. Hybridization is outer orbitals only participate in the hybridization. sp3d2. Nature is paramagnetic. If you write the electronic configuration for central metal atom, we can get magnetic nature. Next, NiCN4 times 2-. So here coordination number 4. Coordination number 4 means 1, 3, 4 are not suitable options for this. Only 2 and 5. In that, this is a strong ligand. Then obviously we have to select this option only. DsP2. Magnetic nature is diamagnetic. So finally answer is option D. In this way, first identify strong ligands and weak ligands. Immediately write the unpaired electrons at the central metal atom. From ligand strength we can get hybridization. Based on unpaired electrons in the central metal atom, we can get magnetic nature. For this 47th question, option D is the answer. Next, the correct equation for spin-only magnetic moment of a transition metal ion is mu s in Bohr magneton. Bm means Bohr magneton. What is the formula? Mu s equal to square root of n into n plus 2, where n equal to number of unpaired electrons. In this type of questions, we should be very careful to get the answer, because number of paired electrons, unpaired electrons, and normally we do not represent this type of notation, whole power 1/2. So to give little confusion, they gave like this. Option C is the answer for this question.